Hi, this is Mrs. Villette, and this video will give you an introduction to continuity, which will then allow you to complete your activity for today. The basic definition of a continuous function is that a continuous function is one that can be drawn without picking up your pen or pencil. And when we say continuous, just the word continuous means continuous everywhere. So this would be an example of a continuous function. Now we're going to add arrows onto the end. That doesn't really count as picking up our pencil. That just counts as saying that that behavior continues. So that's an example of a continuous function. Let me show you some examples of things that aren't continuous functions. So I'm going to demonstrate in this discontinuous function the three different ways a function cannot be continuous. The first way is what's called a jump discontinuity. So you could have a function that's going along and then all of a sudden it jumps and does something else. So I notice I had to lift my pen there to draw that. The second type is what's called a removable discontinuity. So you have a hole somewhere in your function and you possibly even have a separate point corresponding to that hole. And then the third type of discontinuity is called an infinite discontinuity, and that's where you have a vertical asymptote for your function. So here's an example of a discontinuous function, and it's discontinuous for different reasons. So let's go ahead and add on some coordinates. So really I just meant adding a scale on the x-axis. So in this particular function, we describe the three different types of discontinuities. It is actually continuous on some intervals, though. So this function is continuous on, for example, -infinity to 1. It's not continuous at 1 because of that jump discontinuity. It's continuous on 1 to 4, again, not continuous at 1, not continuous at 4 because of that jump or that removable discontinuity. Then it's continuous on 4 to 7 and 7 to infinity. So since we have these four different intervals, we'll go ahead and connect them with a union symbol. A question that you might get asked on a problem like this is, where is the function not continuous and why? So this function is not continuous just at 4 different x values. So at x equals 1, we have a jump discontinuity. It's not continuous at x equals 4. There we have what's called a removable discontinuity. And then again at x equals 7, where we have an asymptote, that's called an infinite discontinuity. One thing that you might wonder is why it might be good to have a continuous function. One of the nice properties of continuous functions that you can apply is called the intermediate value theorem, or the IVT. And basically what the intermediate value theorem says is it says if you have a continuous function, that it has to hit all values between any given two values. So if we look at a function like this, and we know that the function is negative at some point, let's say a, and it's positive at some x value b, then one consequence of the intermediate value theorem would be there has to be a place, let's call this x value c, where the function equals 0. So the intermediate value theorem says if f at a is less than f at b, for a less than b, then there exists c where f at a is less than f at c is less than f at b for c in the interval a to b. Now this also works if f at b is less than f at a. It's still just saying that there's going to be some value c where you can take on any value between those two values. So in this case, this would have been f at a and f at b. So that's one of the nice properties of continuity. Let's look at the types of problems that you might see on your homework. We'll give you some criteria for a function and then ask you to sketch such a function. So I'm going to go ahead and write the criteria down. Then you should go ahead and pause and write it down before we do the example together. So here's the criteria we've been given. Sketch a function with the following properties. Removable discontinuity at 4, f at 4 equals 6, f prime at 2 equals 0, average rate of change on 0, 5 equals 0, and decreasing on the interval 0, 3. Let's add one more condition onto that. So the condition that I've added on is no further discontinuity. So we're not going to introduce any additional discontinuities that aren't necessary. Let's go ahead and begin. We want a removable discontinuity at 4. That's actually not something we can deal with right now until we read all the other information. F at 4 equals 6, that's an easy thing to do. That just means we're going to have a point at 4, 6, an actual fully filled in dot. F prime at 2 equals 0 means that the function has 0 slope at 2. We'll deal with that again in a minute. Average rate of change on 0, 5 equals 0. Okay, so we need to put a point that corresponds to this function at 0. Let's just randomly pick 4. And the average rate of change on 0, 5 needs to be 0. So what that means is if we've got 0, 4, then at x equals 5, we need to also be at 4. Okay, now it also says this function has to be decreasing on 0, 3. So decreasing on 0, 3 means that it needs to always be going down. Now that's going to be a little bit tricky because we also said f prime at 2 equals 0. Typically, when we see f prime equals 0, we're either talking about a constant function or we're talking about the tops of a peak or the bottom of a valley. We're going to have to be a little bit creative here in order to make that happen. It's not going to be a peak or a valley. What I'm going to do is at 2, I'm going to draw a little teeny part that flattens out. And then I'm going to make this function decrease to there. I'm going to flatten it out, and then I need to make it decrease again until 3. I'm going to do something like that. I'm going to erase this little bit. That was just for myself to make sure that I followed that main idea of having it flatten out near 2. Okay, now it doesn't say anything else. I do need to have no further discontinuity, so I need to somehow connect up to this 0.54. I'm going to go ahead and do that. But oh no, we violated the vertical line test because I have a function value here and another function value here. That's where we go back and say that the function needed a removable discontinuity at 4. So at 4, wherever this function was going to be, this little line segment that I drew, I'm going to erase that and put a hole there. So now we have our function with our removable discontinuity there. Okay, I think we've satisfied all the criteria. Now it says that we can have no further discontinuities. So what that means is the function needs to be continuous everywhere else. Let's go ahead and just make the function do something to complete it off. We could have it going to a nice horizontal asymptote. And on the other piece heading toward negative infinity, we could just draw a linear piece and add the arrow to it. So let's go back over and make sure we've met all of the criteria. We needed a removable discontinuity at 4. We have our removable discontinuity at 4. That just means we have a hole in the function, but it's connected on either sides, and we can or cannot have that extra point that completes the function. F prime at 2 equals 0 means at 2 my function should have a tangent slope of 0, so it should be flattened out, even if it's just momentarily or instantaneously. Average rate of change on 0, 5 needs to equal 0. So here's our point for x equals 0. Here's our point for x equals 5. If I drew the secant line between those two, I would have 0 average rate of change. Decreasing on the interval 0, 3. So here's x equals 0, and I'm decreasing all the way down till x equals 3, and then no further discontinuities. So that covers it all. At this point, you should go ahead and work on your activity, at least do the first 2 pages. Those will be checked when I get back.